All right, hello and welcome back everybody to our oreboot and firmware live development streams. Today we're going to look at yet another different SoC than we had seen before, and that would be the Kendryte K230, of which there is two variants, and we will look right into that. We have bootstrapped this SoC already by the end of last year at Chaos Communication Congress during one of the workshops. And today we're going to look a bit deeper into it because I had actually used the 2 hacking days that we had right before FOSDEM with a bunch of firmware developers and ported the DRAM initialization code for it already. And guess what? We could actually already run a Linux kernel on this thing just a few days ago. And yeah, that was actually not even too much effort in the end. We just had to figure out a few nasty bits, if you will. Well, and with those words, let's actually have a look right at this beautiful tool here that we created for this SoC. Because it allows us to just load code right into SRAM and run it right away, which is a very, very convenient way of development. And we've actually developed quite a bunch of these tools right now. So we already have one for the Buffalo Lab BL808. We have a similar tool for an M-Logic, a few M-Logic SoCs and so on. And I actually got to know this kind of tooling through the All-Winner tool. So people from the community have made very, very nice tools so, that you could initialize those chips right away, like initialize their DRAM and so on. They were using some pre-baked blobs for that, but that's okay. But for development in general, it's very, very nice to, have a tool where you could just load your code right into RAM and run it. So with that said, let's actually have a look at that tool here. Where I actually listed a few references to external websites. One is the chip vendor's own website, which gives you a brief overview of the SoC itself. And then there is 2 links to different boards that you can get, of which I actually have both, and we had used both during the workshop at Chaos Communication Congress. But today we're going to focus on one of them, because it has a specific variant of the SoC for which exactly I've implemented the DRAM in it now. And that is already in upstream oreboot even. Anyway, so this here is the tool, and as you can see, there is a fancy logo up here, and that is because, over the last few weeks, I've actually thought about this for a brief while, and you might know I also created this project called Platform System Interface. And that's right, what you see there. So you can also recognize it here in the URL. So in the Platform System Interface organization on GitHub, you now find a good handful of these tools. They're all called something_boot. And in this case, it's Kendryte boot for the Kendryte SoCs. And what this tool then allows us to do is, as I already said, just load code into SRAM, but also a few more other things maybe at some point. We will have to see what we can actually add. So that is, just based on what is implemented in the maskrum. So, each and every maskrum, has some certain code in it, and that may expose one or some other protocol, and that's usually very specific to the vendor. So let's have a look at the boards down here. So we're going to look at the topmost one here, which is the CanMV-K230D-Zero. And the D indicates that we have already baked into the package, there is DRAM. So, we have this chip package, the nice little square thing that you know from your PCBs. And in there is already the DRAM. It's not very much. It's 128 megabytes in this instance, but that's good enough. I mean, we're just, doing bring up here. We're running a small Linux kernel, mostly just to see that it works. So let's look at the board website here. So this board is from Sinovoip, and they make this brand called Banana Pi, like all the many fruit pies, yet another one of those. And here you see the board right away. And if that form factor seems very familiar to you, because it's the Raspberry Pi Zero form factor, hence I guess also the name with a -0 in the end. And you can see there is a row of headers. So this is the same one that you would also know from the Raspberry Pi, and it's also, from what I've seen, mostly pin compatible. So you've got the voltage and the ground pins on the same pins. You've got a bunch of GPIO pins and so on, which means that if you already have one of the so-called heads that you can put on one of those headers, there's like lots of pre-made ones for, like, I don't know, attaching screens, or I don't know, microphone arrays or buttons, or certain cases which already have some extra stuff. That should just fit on here. And I myself, I've actually bought a case which was made for the Raspberry Pi Zero, which usually has the micro USB port. So, well, you have two micro USB ports, but this one here, as you can see, has two USB-C ports. So, they are a bit of a different size and slightly different form factor. So I had to use a file to, extend the holes in the case a bit, and yeah. But whatever. I guess not everybody is doing that anyway. But I found it very nice, so I didn't have the raw PCB floating around in my backpack when I was traveling. Anyway, so we're using both of these ports here, and let me tell you what they are for very briefly. So this one here, that is the USB on the go port, and on that port you have the mask-ROM's functionality exposed. So when we connect this board, then, when you have this thing connected, you will see this port show up in, let's say, LSUSB, for example. But you will still need power for it. So if you only use that port, that will not work, unfortunately. The other port here is for both power supply, and it gives you a USB serial converter. So I'm not sure where the converter is. I think it's on the bottom side of the board here. So yeah, I need to actually connect both of those. And I'm using my trusty USB hub here, which has like single switches for each and every port. So I can conveniently turn this thing on and off as I want to. Which means I can actually already present you right away how I'm turning this thing on. And then I can already load my code and run it. And let's actually do that right away, just to get a bit of a kickstart here. As you can see, I have many things open. I'm very sorry. I have a Cosmic Desktop environment now, and unfortunately, the window picker here isn't yet, as easy to use. So, anyway, I was actually trying to hide that by having it on the other desktop here, but yeah, never mind. So, what we have here is, well, I have two terminals here, multiplex on my screen. On the left-hand side is a directory with an oreboot, and I will show you which directory that is right away. As you can see, it's here in my projects directory where I have oreboot, and then under oreboot, I actually have, a good bunch of Git work trees, so I can, work on a bunch of things in parallel. And we're actually going to use that a bit later today because I want to extract some functionality that we can use in a shared library. And we've already done that just recently with oreboot. So if you've been following the changes, then you might have seen that we now have a few convenience helpers for, doing memory mapped IO access and stuff like that. Also like memcopy and memory testing. So yeah, this is now my big work in progress work tree, which actually has a good few commits. As you can see here, it's 180 commits now. This here just means it's not yet synchronized with my counterpart on GitHub, but yeah, nevertheless, as you can see, it's a bunch of changes. It's essentially all I've accumulated over the many years, and I've been working with, I don't know, like 3 or 4 different SoCs now, so all of that stuff is in there. Anyway, so we are in the mainboard directory, and the SoC vendor is Canaan, and the board is called CanMV-K230. Well, never mind the line break here. And so in that directory, just like for every other platform, we have 2 main directories. So we have the BT0 directory, or boot 0 to expand it a bit, and that would be the very first stage. That is essentially what we then run in SRAM, and this is where we initialize the DRAM controller, and we initialize DRAM just so that we can load our other code to it. And that's all we're doing in there. I mean, we also print out some information and stuff, right? So we need that for debugging and development. Yeah, but that's not really a goal. It's just a necessity. The only thing we really just want to do is initialize DRAM. Once we have that up and running, we would load code into our DRAM, and that is coming from main. So main is actually the main environment of oreboot, and that is for RISC-V, where we set up something called SBI, the supervisor binary interface. And that is what operating systems like Linux, for example, would rely on nowadays. It's essentially like a BIOS in the 70s. They just gave it a different name. And to accompany all of that, I have created this makefile. This makefile, will give us some convenience tasks so that we can run it. I will show that in a bit. And then I started drafting a README that is not yet upstream. And, this is actually where I'm essentially just giving instructions on how to run oreboot, which is exactly what I'm also going to show today here. So yeah, let's actually have a brief look at that. So this is just a rough summary of what I just said. Yeah, we are talking about the K230D today with 128 megabytes of built-in DRAM. The other chip variant without the D, well, that has external DRAM. So, you would find some DRAM chips on the PCB. And in order to run oreboot, well, you need the Kendryte boot tool as of now. So we don't have support yet for running from, like, let's say an SD card or SPI flash or something, nor the tools to flash that or something. But that's okay, right? So we're mainly doing development here. So you would clone that repository, and I had also created a test payload, and this test payload here is just called SBI test. I think I've actually showcased that before. It just does something very, very simple. It does a few prints using the SBI as an interface, right? So it would do a bit of console output, like, printing a few characters. I think it just prints a test, right? Then it would enter a loop, and it would just keep printing loop, 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 just nothing else, just doing that. But it would also set up a timer. And this timer will then be used so that we get interrupts. So SBI defines that in its standardized interface. And when you set a timer, at some point you would get the interrupt, and then we just print something else again. Well, we just print interrupt, right? And that's actually all the primitives you need for having an operating system. So what you would need is, you would need scheduling. That's what you use the timer for. You would need I/O, or input-output. That's what we just use the console for, to give output. And then you would need compute and memory resources. I mean, we have a processor and we have all the DRAM available. So you have all you need for, just creating a very, very tiny operating system. So yeah, that's essentially the proof of concept to, showcase that an SBI-based system would actually work. All right. So, and then I have created, two very convenient make variables here. I actually created a third one. It's not yet mentioned here in the README. So one is, just to point to your installation of Kendryte boot. So you can have it in your Unix-style path environment variable so that you can write right away, which I have here, for example, right? So I can just type it out, as you can see. And otherwise, you can use this make variable. And then we have a variable called payload. And that is what we would then use to point to our payload, which could be this SBI test here, or, as I just get it to work, a full Linux kernel. And, then, of course, with Linux, you would also need a device tree. Unless you have that built in, you would also use that environment variable, make variable. I will show that right away. And that is what you see in the makefile then. I also added the link here to the technical reference manual, so that people can look up, like, details on the SoC, how certain things work. Maybe you want to develop something or whatever. So let's have a look at the makefile. It's also not too complicated, as you can see. The above here is essentially boilerplate code. We will at some point actually get rid of that stuff because it's, like, really unnecessary. These are just targets that are currently sort of mandatory just because of the general setup that we have in oreboot. But yeah, never mind that right now. So what we are interested in is actually these few targets down here. So we have this target called mainboard. So mainboard, would just invoke build, and build again would do two things. So it would build the BT0 target, and it would build the main target, and those two here, well, they just call in to make again. And let's actually make a little adjustment here because it just comes to my mind. So in make, just by convention, you can actually use a variable called make itself. And that means, you would actually use the make that has been used to invoke the make here, so or the make file. So let's apply that here and there, and also here, and there we go. And so as you can see, I have a few more extended targets. So I also have run BT0 and run main, which means I'm not just building those, but I'm also running them. And to run them, I have make files in the other directories as well. And they would then, just use the Kendryte boot tool in order to load. And down here, you can see I have yet another extra target, and that would then load two things. It would load a payload and a device tree blob. So that is essentially what we use to load the Linux kernel. So we would use payload to point to the Linux image file. That's what you get when you build the Linux kernel, and then the corresponding device tree. And I've actually had to create one, based on some code from the vendor still, because the upstream Linux kernel doesn't have a device tree yet. But it wasn't actually too hard. I could actually use very much the vendor's code right away. I just removed a bunch of things which are not yet able to run in the upstream kernel because the drivers are simply not there yet. But I've actually seen there is a few things happening right now. So slowly, just one after another, there will be more patches trickling in. So as you know, Linux is being, developed by many, many people all around the world. And it just takes a while for, patches to reach the so-called mainline kernel. So essentially what you get from kernel.org. All right. You can also see the addresses where we are loading the respective files. So you see right here, we're actually loading this to a very, very low address, and that is because the DRAM space actually starts right at 0, which has a bit of a caveat. So there is one thing we cannot do, and that is just, because how pointers work in many environments, we cannot really use the address 0 exactly, so we're losing a few bytes there. But yeah, never mind that. I'm just running our code, at a certain offset. You can see that right here, but yeah, never mind that. And this here is really just a convention thing, if you will. Just running whatever your payload would be for the SPI-based environment. You would just run that at a 2 megabyte offset. It's also what OpenAI SPI does on most platforms, if I'm not mistaken. Anyway, so then I have the run target, which collects like all the other things. So it would run BT0, it would load the payload, and then run main. And that works as follows. I have some code within BT0 so that, it would actually jump back to the maskrom and then let me load these other two files. So, those two up here. All right, so let's have just a brief look at the not this makefile, but the BT0 makefile. So yeah, as I said, it's essentially just as simple. You see the same stupid boilerplate code here. It's not really necessary to have all of that here, but yeah, never mind that right now. Essentially what we're doing here is, we just use a cargo build to build this target here, and then cargo obj copy to, just create a flat binary. And this binary that we get out of it, well, it's placed in the, just target directory that we would otherwise use. At some point, we will integrate that also in XTAF, so, it will be a bit simpler than this here. But yeah, this is good enough for a start. Then we have the option target to, look at the compiled code, so that you can see the assembly of it, and the run target, which depends on the build target. So what we would do here is we would use the Kendryte boot tool and then just say run and point to the binary that was created. Alrighty, and let's actually, oops, we're not in Vim here. So let's actually do that right away. So what I'm going to do now is I'm, turning on the USB port here where I've connected the board, and on the right-hand side, see the message is now actually gone. So yeah, I'm connected back to the serial port that is, behind the USB serial converter that is part of the board. And yeah, we're now going to run our code on it. So you see, I already prepared this command here. So we're saying make, well, as we should, and then we're setting the variable payload, and we're pointing to a kernel. Never mind the path here. It's, currently, because, for Linux, I'm also using like, multiple work trees and such. I just haven't cloned that yet to a different directory. So it's sitting in my softcode directory, but whatever, it's Linux. So in Linux, we look at the arch directory for architecture. Under that, we have RISC-V, because we're on the RISC-V architecture. And in the boot directory, we have the file called image, and that is also a flat binary. That is what you get when you build the Linux kernel. And then we point the DTB variable, to the same basic directory again. And in that, also in arch RISC-V, we now have the subdirectory boot, in which we have DTS for device tree source. But that's not only the device tree source, it's also where you get the device tree binary in the end. So now you have the same structure again. So you have Canaan, that's the SoC vendor. And then you have K230 CanMV, that would be the board, and .dtb as the extension. Well, and finally the run command. So we're essentially doing make run with those two variables set. So I'm doing that right away. So as you can see, we're building the code, and on the right hand side, you already see it says oreboot BT0, does a few things, and now it gives you this error message. But that just means we're going to load some more code. And lo and behold, it's actually so fast right now. We're already in Linux. So we just booted into Linux within, I don't know, 3 seconds or something. It's the fastest boot experience that we have as of now with the oreboot project, and Linux on top of that even. So yeah, it was so super fast. Let's actually scroll back a bit because it was really quite a lot. So back up here. So this is where we have BT0. The above was, from a previous run, so just ignore that part. So we're seeing, this is running on a T-head platform. So T-head, or actually XuanTie right now, that would be the vendor of the core. And the core is a C908. If you remember, we were running on a C906 core when we looked at the Buffalo Lab SoC, the BL808. So this here is a bit of a different core. And what's a bit special about that one is we actually get to use the vector extension 1.0. So that had been standardized at some point in RISC-V. And the C906 didn't yet have the version 1.0. It had like a pre-release version that was 0.7. So yeah, if you want to play with the Vector 1.0 extension, this might actually be the right platform for you. And as you can see, we can boot Linux very, very easily, which means you can actually very nicely experiment with it, right? So you already have Linux running. Anyway, we're printing out some more information. So because it's a XuanTie platform, we also get to have the CPU ID register, which is a bit special. You read it like 7 times, and then you get 7 different values out of that. And we actually have a tool for that in the platform system interface project that you can use to decode those values. Yeah, I'm not going to do that right now. That's for another day, because we want to look at what we've booted up here. Yeah. These messages here are actually from the DRAM initialization. It's mainly the same messages that the vendor also had. Some of them look a bit redundant, so yeah, whatever, never mind that. So the DRAM initialization was done, and it took this much of time. I actually don't know what time unit that is, right? So this is just what I get from reading the M time register. And now it gives you this error message. And where does this error message come from? Well, that comes from the mask-ROM. So when you boot up this SoC, we haven't seen that because it took a while for the serial converter to actually attach. So we missed this message initially, but it came out as well. So yeah, if you don't believe me, just get one of those boards and do a reset. I can't do that right now because it's in the case and I can't reach the buttons for it. But yeah, you would also see this message, and this message really just means the mask-ROM could not boot from any given resource. So, it would be trying to, I don't know, boot from a flash or boot from SD card, whatever. And if none of these are available, it would then fall back to USB mode. And we can also look at that briefly in the manual in a bit. We're going to look at that anyway, because I want to show you, a few footguns that appeared right during the development. It's something you just need to get used to when you do firmware. There is a bunch of things that can just easily go wrong. So yeah, anyway, so we are printing out the same information again as above. I may actually remove that from the initial stage because it doesn't really make sense to have it twice. Or maybe we'll print it here in a different way, or maybe, I don't know. I think it actually makes sense to have this information very early on already. But then again, we're mostly interested in setting up the main stage here. So yeah, I haven't really decided on that yet. Anyway, so we're doing this here. And this is now the first part where you need to pay attention. We are setting up a few so-called CSRs. What are CSRs? They are the control and status registers. That is a RISC-V thing. If you know other platforms, you may have heard MSR for x86, for example. That is essentially the counterpart, if you will. So that is special per platform, and by platform we mean the specific hardware platform. So the specific SoC from a specific vendor, which are actually necessary in order to run systems because they have certain assumptions about the environment they're running in. And what we need to set here is, for example, we need to grant access to a few resources to the Linux kernel. For the XuanTie platforms, we need to, enable some extra management features for memory, stuff like that. And that is what I want to provide a shared library for at some point. Yeah, we need to figure out still, with a different T-head cores that you can get and the different SoCs, how they are using them and so on, right? So in order to generalize that, we still need to, gather some more information, get some more experience with these platforms, right? And then we already set up our SBI. So part of the SBI is the trap vector. So MTVEC means machine level trap vector. And the trap vector is essentially, well, for us, it's a single entry point. We're, not using the vectored mode, but the simple mode. That would mean whenever a trap occurs, and by trap we mean two things. That would be exceptions and interrupts, as they are standardized by RISC-V. When one of those occurs, we actually get back to our M mode code again, and then our trap handler would be running, and it would then need to decide what to do with the exception or interrupt that is given. And that is, for example, how we handle the timer interrupt. So for, setting a timer, there is an SBI method. The system, in this case here Linux, would be setting a timer that would then use the eCall mechanism that is in RISC-V. Then we would get a trap in M mode. We would see, hey, there was an eCall. eCall means environment call. And that now says, hey, set a timer for us. So, there is a few registers used just conventionally. One of them tells you which method you get in SBI, and the other one which value. So you read out the method and you see, oh, it's the set timer method. And then you see the value, and now you know what value to give to the timer. So we set the timer then. We enable the interrupt for the timer. And then we just pass back to the S mode system. So that would then just be running and running, doing its thing. And at some point we would get an interrupt. So our trap handler would be invoked again. And we would see, oh, this time we actually got an interrupt. Which one was it? It was the timer interrupt. Then we would set a certain bit for the S mode again, clear our own bit. And in S mode, we would then get the interrupt again. So the S mode interrupt handler would then need to take care of that part. It seems a bit weird and redundant, to be honest. I'm not exactly sure why the platform was designed that way, but as I got to understand it, it was so that you can always virtualize a RISC-V platform. Though yeah, it just feels a bit like, I don't know, maybe it wasn't really meant that way originally. I don't know. Or maybe they forgot about it and, just retrofit some idea later. Anyway, yeah, I don't know for sure, so I can't really tell. It's, just my own thoughts here. So yeah, with the rest of the setup here, we set up the delegations. So with a delegation, we can actually pass down a good bunch of traps to the operating system running in S mode. So we don't need to handle like all the exceptions and interrupts. Doesn't actually make sense for, a bunch of reasons. We enable our own interrupts here. So yeah, MIE means machine mode interrupt enable. Yeah, we're printing out the ISA string here. That doesn't really matter right now. We set up memory protection, so we have a range here that is actually protected, so that the operating system cannot accidentally write to it or execute our code. Well, it can read the code. That is just fine for us. We don't have anything to hide in here. Yeah, but it's important that it cannot be overwritten, because then the system would actually sort of crash itself in a way. Unless it really knows, what to configure there to, I don't know, replace our code or something. But yeah, it's, a possible foot gun. So we actually apply the memory protection here. So PMP is for physical memory protection. Yeah, the last range is essentially just disabled. Just ignore that part. We might actually improve the printing of the addresses here. It's not really as nice yet as it should be. Well, then we prepare the supervisor, and that just means we're setting up two registers, just as a convention here. We're passing the hard ID and also the address of the device tree to the S mode environment that we're then calling into, in this case Linux. It's loaded at this address here. Well, we could also print the 0x here and also here. Yeah, never mind that. Anyway, we're saying in a loop, and then we are already in Linux. So you get the first nice message from Linux. It says Linux version yada yada yada. We got my nickname in here because it's my custom kernel build, so I put that in there. Yeah, some information of my build host. So yeah, whatever. Then we get the machine model. So that is something that we have from the device tree. So this, when Linux boots up, one of the main things it's actually doing for a device tree based platform is it would read out and parse information from the device tree. Part of that is also which console to use, for example, well, the model, as you can see, and a handful more things. And this is actually important to understand. So in Linux, there is a good bunch of options for the kernel, and one of them controls how to use the kernel command line. So you can get the command line from the firmware. Well, from the firmware in that sense actually means that you would read it from a device tree. In a UEFI-based system, I think it would be read from, some table or something probably, or a pointer in a table that, just points to the string. Well, in our case here, it's in the device tree. We could manipulate that device tree from within oreboot. Well, we currently choose not to. It's something we're going to implement at some point probably, because we will also actually need to pass the memory ranges from oreboot to the system, because the kernel cannot possibly know it. And then we, what were I gonna say? Yeah, the thing that you need to understand is you need to already parse all of that information and do a bunch of other setup in order to get the first output from Linux. So all of this stuff that you can see here is actually quite late in the kernel, to be honest. In order to get like really, really early output, you sometimes would need to do some fiddling to get, more debug output. And you might need to configure the command line so that it actually ignores the device tree. Because the following happened to me. I had pointed to the wrong address when I loaded the device tree. Linux tried to parse the device tree. I also put something in the Linux command line that is part of the kernel configuration that says use the SBI console, as an early console, and then, parsing the device tree obviously should, have errored, but I never saw any message whatsoever. So I assume something, is still a bit going wrong there. I would call it a bug. I don't know. I will see. Maybe I will talk to some kernel engineers and see if we can change that in a way, because it's really hard to debug that stuff. Anyway, so yeah, when I had figured that out, by just hacking into the Linux kernel actually and doing like lots of early prints, until I got to the point where it broke, I was like, oh right, that was just after parsing the device tree and so on. So yeah, I was getting a bit more suspicious again. And it was actually crashing when trying to set up the virtual memory at some point. And that was because it didn't actually know the memory range, because if you remember, that is part of the device tree. Anyway, with that mouthful here, let's just scroll way further through this here. So, you get the usual output that you get from Linux early on. Like, you see the memory range printed here. This is coming from the device tree. Again here, I don't know, it's a bit redundant. You get about a bunch more other stuff here. So like, all of this stuff here. This is essentially the kernel memory layout. It says so here, the virtual kernel memory layout. So because the code here is running in S mode, you can actually use virtual memory. You can't use virtual memory in M mode. So that is why you would usually run a virtual memory system, well, in S mode, because otherwise you can't use virtual memory anyway. Yeah, a bunch more things are happening. And then you can see at this point here, it's enabling the legacy console. And that would at some point take over. So, the first prints came from the SBI console, and at some point, it would then take over and use Linux's own implementation of the console. Alrighty, so a bunch more things here. And now you can see, yeah, here, this is where we're now switching to the boot console, from the legacy boot console to the TTY-S0. So TTY-S0 is Linux's own driver using the same interface here then. And right after that, we get the next drivers attached. So this one here is actually pretty nice. So in upstream Linux, there is already support for the designware USB 2 controller. So DWC, I think that is for like device designware and controller 2. I don't know. It's a bit weird. Anyway, so it's the USB controller. So designware as in, the product series from Synopsys. That is, essentially the duopoly, if you will. So there's two suppliers, Cadence and Synopsys, and they're selling like all the peripherals to the SoC vendors, and then they just reuse them instead of designing their own. That also happens sometimes, yeah, but mostly they're buying from those two vendors. You can read up on them on Wikipedia or something. Right, and this USB thing here means we can actually use the USB port to have a direct connection from our system, and that's how we do it. I'm setting up the USB Ethernet gadget, and USB Ethernet gadget means I can now actually run a CPU daemon on the other side and then CPU into it from my system. If you don't know yet what CPU is, please go check out our previous videos where we introduce what CPU is and played around with that quite a bit. Anyway, so we get here. This here is the CPU banner, unfortunately garbled a bit because we get this message interfering here. But yeah, you may believe me. This is saying CPU and then an exclamation mark. And this is now our initram file system. Our initram file system is created with uroot, the universal root file system, and under the uroot project, we actually also have the CPU project. So you find all of that in GitHub, and as I mentioned, we featured it in earlier videos already. So yeah, I have a static IP address configured here. We would normally be running a DH client, so like, to get an address via DHCP. Yeah, but I've actually created a little shell script that would be running on startup that removes the DH client binary here and then gives me a static address. Well, and then we would be listening on our default port, and well, since we're booted into the system and we also get a shell spawned again by CPU, we can now type something. Let's say we print our uname, right? So whoopsie, that was meant to be an A, not an E. So we get all the information. So we get Linux again, my nickname and stuff. That is essentially also the information that you get from, the first message that you get from Linux. You get the build timestamp. So that was built on a February at a very certain funny time point in time. Well, we're running on RISC-V 64, and I think none is like the default host name. This is now my host name. It's CRV, short variant of my nickname. Anyway, so what we can now do is we can, as I said, CPU into the system, and let's actually use the command that I pre-built here, and let's actually do something simple. So we're going to cat/proc/ let's print the command line. So CPU, you can imagine that a bit as like SSH on steroids if you don't know that yet. So this is now getting the information from the other side, and we get the output here. So this is our command line. We have the early console that is using the SBI. Then we have the real console that's on TTY0 or TTY-S0 respectively at this baud rate. We have a log level, and here we have our Ethernet gadget set up. So yeah, that is how I, on the other hand, get to see this here, right? So this here is the USB Ethernet device, and as you can see, we got this address on our host side. And yeah, that again is also statically configured. So yeah, on my host machine here, in my network settings, I also just configure that address. So yeah, that's how it works. In theory, we could now also run any binary that I have on my machine right here, but that currently crashes the kernel for us. I'm not sure yet why that happens. It should not, of course. Yeah, it's probably a bug somewhere in Linux. Anyway, so yeah, we got this up and running. Of course, we could also do some other stuff, right? So we could also just spawn a shell, for example, right? So yeah, we get this prompt here. We do not have a path set up here, so I would need to write the full path to the binaries here. And let's say, I don't know, we list our files. And now I'm listing files here, but this might actually confuse you now if you're not used to CPU. So the files I'm listing here are actually the files that I have in this directory here on my host machine. And that is because I'm taking my local namespace with me. So I'm mounting both the my home directory here and also my projects directory. And that means I get to see them on the other side as well. And as you can see here, I'm actually in the same path here. So this path here in my shell is also what you saw up here. But of course, I can also show you that we're actually not on my host system, and that is by listing the slash directory. So what you see here is some things that you wouldn't see on my host system. For example, the bbin directory, which is where we have like all the binaries from our initram file system. Well, most of them are actually just symlinks, and that works as follows. very similar to BusyBox if you're used to it. So all of these commands, they actually point to this one single binary called BB. So that is actually, a rather big, not too big, but a rather big binary, and that knows all these commands in just one file, which gives you a very, very efficient build, because it means, you don't need to actually have like duplicate code for doing a bunch of things, especially with Go, because all of this is written in Go. You would usually have the Go runtime in each and every of those files. So yeah, in this case, you don't have that. You actually have only one single binary. So I actually have a look at the BB file and see its size, and that would be 14 megabytes, right? I'm not sure if we have human readable print. Yeah, we do. Yeah, so yeah, as you can see, it's 14 megabytes. It's actually the biggest part in my kernel right now. So I think the whole kernel image is currently like, I don't know, 17 megabytes in size or something, right? So the kernel itself is actually rather small. It's really just a few megabytes. Anyway, the good thing is the initram file system is actually also rather small, because we've compressed it. And yeah, through compression, and if we also compress the kernel itself, we actually really do get down to a few megabytes. Yeah, I just cheated a bit by saying it's only 3 megabytes, but that's not really the case. It's actually much, much bigger. So I think the whole kernel image, like including the initram file system, is currently 17 megabytes. And yeah, with like, both the compressed initram file system and the kernel compression around that, I think we could get down to, I don't know, maybe 8 megabytes or something. So it would actually easily fit in a SPI flash. Anyway, so what else are we going to do? We're now going to look a bit at the code, because now we'll turn this thing off for the time being. We're going to look at the code because I want to show you a few things that we ran into. And with that, I will also take a look at the data sheet. Anyway, so I'm currently using the Z editor for, just working on Rust things. It actually has some very nice integration with it. Yeah, anyway, so let's have a brief walkthrough. So let's look on the left-hand side here first. So this is our Rust code, and this is our main file for the boot 0 stage. So up here, we have the usual setup. So what we do here is essentially, we're storing the current program counter in the S4 register. That is just so that we can get it out again later, and print what the original program counter was. That is very useful, for example, when you run on a foreign platform and you want to know where your code is actually running. If you just run somewhere in SRAM and you don't know where in SRAM exactly, that would then help you, because that really depends on the master RAM, how it loads your code. Well, then we, clear all the status registers and disable the interrupts and stuff. Yeah, after a while, we then would just, say we jump to our reset function down here. Right, so yeah, for every hardware thread, that is the RISC-V terminology for, essentially like a real thread in hardware on a given core. We would then just be waiting for interrupts on every other hard but the main one. So we use one that is, used for booting the system, setting up the DRAM and everything. The other one is currently not in use at all. We would need to implement that at some point. So we head over to our reset function. Yeah, we're doing a few setup things here. We actually need to have a better setup around that. So you would usually use that to clean up or prepare your RAM that you're gonna use. So in many systems you would actually run your code from right from a ROM. So for example, it could be running from SPI flash, that is essentially then mapped like a ROM in memory, and then you would use RAM somewhere else. Yeah, but in this case here, we actually have one flat image and it's already in RAM, so the RAM is already prepared. So we don't really need that part here. Yeah, I took this from the Rust embedded Embedonomicon, so that would tell you how this stuff works on a microcontroller. Our system is very, very similar to a microcontroller, except that we have a DRAM controller, and we've got like a bunch more memory space to use. Anyway, let's skip that. From there, we jump down to the main stage. Anyway, and what you see down here is our main stage, setting up the UART, doing a first few prints, then invoking this function here, and we'll get back to that in a bit. Yeah, this is what I actually took from the vendor C code. So that would do some setup with the clock management unit. Yeah, this is where we print our extra IDs, as you saw, right? We print a bunch of information. Actually, we then do the DRAM in it, print that we're done with it. We might do a bit of a memory test, testing different ranges here. Yeah, I'm currently skipping that mostly. And then we already execute our payload, which would then actually be the loader here. And what does loader actually refer to? Well, it is the maskROM base, and maskROM base is really where the maskROM code starts, and this loader is what would be loading code over USB then, and then jump to it. Very convenient. So yeah, and that is why the last thing I have in here is wait for interrupt, and that would really just happen only in the case that we actually came back from executing our code here. But from here, we would actually already jump into our main stage. So yeah, we should actually never get here. All right, and now up to this function here that is called enable mtimer clock. So somebody found that somewhere in the vendor's U-boot code, there is a few lines for doing exactly the same stuff here. And there is a comment in there saying enable mtimer. And that is what we're going to look at the C code over here. So this is the vendor's overlay for U-boot, which has like the specific code for their SoC. And as you can see here, there is this comment, enable mtimer clock. It's been somewhat recently modified. I don't know. It might have been rebased or something. Anyway, so what it does is it writes a 1 to these two registers here. So one is for CPU 0, the other one for CPU 1. By that they mean hard 0 and hard 1. And then they enable this other thing here. It's called STC0. That is just another timer. You actually have a bunch of timers on this platform, so yeah, I don't know. They're also doing this here. I have no idea what that is, or I just don't recall it. Yeah, you can find all of that stuff in the manual essentially. But what we're going to do now is we're going to switch over to the manual, and we're going to have a quick look at what these registers are. So keep in mind the base address of these registers, which is 91108000. And then we have a 20 in the end here and a 30 in the end here. Well, it's hexadecimal, but yeah, you get the idea. Alrighty, so with that, let's have a look at the manual. So the menu starts, with a few lines of description and so on, and I already scrolled down here to the boot and upgrade modes, and this is where it says, what I just told you earlier before. There is a few boot media that you can use. You can use a SPI flash, an SD card, eMMC, and otherwise it would just fall back to the USB port, and that's what we use for booting our code. And yeah, it doesn't actually tell you the protocol for it. But the vendor has their own tool on GitHub. So I actually just took their code, and then just wrote my own based on that, to fit my own needs essentially. Well, and after that comes the address space mapping. So this is now the memory map. And in the memory map, we're now going to search for the address that we just remembered. So we had 91108000. Aha. It says STC, right? So let's have a look at this again. 91108000. I first thought it was some sort of debug register, but yeah, whatever. Let's see what STC actually refers to. So STC, unfortunately, I can't just click on this. Do we have a chapter on the STC? Yada yada, yada yada yada, yada yada yada. There is this chapter here, STC timer configuration. Do we get to see, oh, right. Here. So STC timer register base address is the base address. That is what we had in the memory map. And we need to look at those two offsets here. So we have STC2, that is at offset 20, and STC3 at offset 30, right? So those are these two addresses. And we might actually already obsolete the statement here saying we don't know why, because we might figure out why right now. I misread the memory map earlier and I thought we were actually somewhere else. Alrighty, so let's take a look at the elaborate description. So we are in which chapter? 2.6, timer, function description, register summary, register description. All right, so we need to find our offset, hex 20. This is B0. This is A8. Did I already scroll past it that quickly? Oh, interesting. Right, so it says timer N control register. So the control register for timer N. In our case, that would be 2 and 3, as we just read earlier. And so we would have hex 8 plus N minus 1, because, you know, we'd start counting at 1, but, you know, on the machine, we actually start at 0, times hex 14. So hex 14 means for each timer we would have 5 registers, right? So each of the registers would be 32 bits or 4 bytes wide, and hex 14 means it's 20 bytes. So hex 10 is 1 times 16, right? So each and every digit is for like powers of 16. And yeah, so that would then sum up to 20. And 20 by 4, so 4 bytes, the register size, means we have 5 registers per timer. All right, and what does it actually mean? Well, the first, like all the highest bits are actually reserved bits, so they're not in use. And well, we're setting the lowest bit, and it says timer mode. So what does timer mode mean? It means user-defined mode of operation. You must set the timer 1 load count register to all ones before enabling the timer in free running mode. Okay. Interesting. Oh wait, no. I just misread once again. I always messed this up for some reason. So the lowest bit, of course, is not bit 1, but bit 0, right? So we're just writing a 1 in this bit. And this means enabled. Timer N is enabled. So for whatever reason, the timer that is also called mtime in RISC-V is actually mapped to this thing here. Interesting. So what we really do is we enable timer. What was it? Looked a bit different earlier, didn't it? Where was hex 20? Here. Right. Yeah, so this here is like a general description with the calculations. And down here we have the detailed description. Huh. That confuses me a bit. Hang on. So we have 0, 4, 8, 20, 24, 28, 30, 34, 38, 40. There is some gaps in here. Okay, so we really just have 3 registers per timer. And they started the calculations at offset 8. Weird. What does it say here? So 0 would be load count, whatever. 4 would be current value. 8 would be control register. Current value is a bit weird because the timer value should actually be like 2 registers. Like you would have a 64-bit value, so you would have I don't know how that works. Weird. Yeah. We might figure this out. So 0C would be clearing the interrupt, and then this here, but that does not actually map to what we see down here, does it? Like hex C is missing here. And also hex 14. Well, hex 10, hex 14, and so on. They're all missing. I don't know. That's a bit weird to me. Right, and here, as I said, right, so the timer values would be 64 bits, so you have 2 32-bit registers, and then you would need to, you know, add them together. Huh. Interesting. Yeah, I don't know. These manuals can be very, very confusing at times. I don't know why that is the case. Anyway, so yeah, we will just stick to this here. So we can name those registers and call them STC2CF. Whatever, copy paste doesn't really work. STC0CFG, like that. No, that was 2. And then we have STC3CFG. We need the same thing here. STC2, STC3. We don't know why, but this enables the M timer clock. It is apparently backed by the STC. So STC is something timer clock. I don't really know what the S is for. I just guess the T is for timer and C, I don't know, clock. Yeah, I also don't really understand why there is like STC0 in here, but not STC1. I mean, just following this here, I would expect STC1 to be at hex 10. But then again, here it says like each timer block would actually have 5 registers, so it would be like hex 14 and hex 28 and so on. I don't know, it's a bit weird. Yeah, I can't make much sense of that right now. I would just leave it at that. It's still a bit of a mystery. Anyway, so without setting this part, and that was an issue I had earlier, the timer would actually not be running, so it would be stuck at 0. 0 means we will never get any timer interrupts, and that is why when I ran my SBI test first, I was just seeing my loop, and I was seeing my loop, and I was never actually seeing my interrupt. So yeah, I need to figure that out. I needed to figure that out first. Whatever. So yeah, that was one of the foot guns we had. Now let's look at the next part. So we are now looking at our main stage. Our main stage is also rather simple. Well, we have a bunch of imports here. They don't really matter as much. We have our platform name up here and so on. We have the same setup that we saw earlier. Again, we need to I think we might actually eventually remove this or make it like conditional, like, you know, depending on how we actually boot the system. Now booting from SRAM, we don't need this part. And then we already have our main function down here, which is, as you can see, really not much code. Again, we're initializing our UART, we're printing out some information, and then we already jump to executing our payload. Yeah, we'll come back to this function here. Whoopsies. The init function, because that is something, we will look a bit in detail. Anyway, so executing our payload down here works as follows. So we have our payload address and the device tree address. I think we can ignore that part as well. So yeah, that is again some more CSRs for future us. I think I've disabled this here. Yeah, it's set to false. Yeah, we print some debugging information so that you can actually see like, the payload and the device tree here. What we then do is, in the case we're using SPI, so this is just hard-coded to true for the time being, until we're done with the development. We would set up the SPI runtime, essentially. There is a few more things involved here. And then we would run this here, which is execute supervisor from our SPI library. And that is already where we jump right into Linux. And yeah, as I told you earlier, we need to provide the hard ID over to Linux and also the device tree address. So yeah, this is what is then passed on by the execute supervisor function. It's just put in the right registers. Alrighty, I think I skipped the part where we're actually loading the code to RAM. Was it in the boot 0 stage actually? Did I skip that? Because we do need to have that somewhere, right? So, oh, right. No, that is actually that is actually from our maskram. So the maskram has like a few different methods. One method is to just load something, and another method is to run something. So you can load a bunch of binaries to different addresses, and then at some point say, hey, run the code at this address here. That's how it works. So we don't need to have extra functions here. We needed that on a different platform, but we're not going to talk about that one today. Alrighty. So yeah, back to this here. And by the way, if anyone is writing in the chat, I'm not really seeing the chat right here in OBS for some reason. I will have a brief look over on Twitch. Yeah, the only message I got here was some sort of stupid spam. So yeah, we'll just ignore that. Anyway, yeah, back to our main code here. So yeah, as I said, we're executing our supervisor, and that would just be Linux for us. Alrighty, and now back to some of the setup. So I told you this here is a XuanTie platform, right? And the XuanTie platform has some special CSRs that we also need to set up. And I do have the corresponding code for it, and that should actually be up here. Right. So yeah, in exec payload, we have this function. We want to look at this function. So this function initializes, the one that you saw up here, well, it's just doing some debug prints if configured to do so. And then it would run this function here, initializes, from our work in progress development thing called XuanTie. And down here, you also see the print CPU ID actually also comes from that. So let's actually have a look at that, right? So over here, I have created a good handful of helpers. And those helpers are a bit special because they only actually apply to the XuanTie platforms. So one thing you can do is you can read this thing here called MAPB adder. So M for machine mode again, so you can only read this register in machine mode. And then APB, I would guess that is for the APB bus. So yeah, I put some notes here. I'm not sure how accurate that is. Anyway, so this will give you the base address. I was at some point misreading that as bad address or something. I really didn't understand it, but now I do. So that would give you the base address of the platform level interrupt controller, or PLIC for short. That is a standardized part in RISC-V. So usually you would find that in the memory map, and you actually also do find that in the K230 manual. But you don't actually need to know that up front. You can read this base address from a CSR, namely that one. So let's see where this function is used. It's used down here, and it's used for a good handful of functions. So first of all, it's used for the getClint base function, because it's exactly the clint base. Well, it says plus clint base offset. Well, it's not really the clint base. Yeah, you still need to add this number to it. Yeah, so this here is a constant, and if you want to know more about it, you can look at the C906 and C908 manuals respectively. You know, they document that stuff. Then you saw this, well, this function is then used in these other functions. So yeah, these are essentially the registers that are based on the clint, and these are now standardized offsets. So there is one for the mtime compare register. This is where you set the value when you get the set timer invocation through the SPI. And then we have the mtime offset. So mtime is the register that you can actually read in order to get the value. So yeah, you can, so this is actually funny. So this is one mapping of the timer. So you can read the current time from this register plus the next register. So it's actually, you know, because you have a 64-bit value, you would read two 30-bit registers, and you should really do that on these platforms here. So you would need to add them together and stuff, or, well, shift and or, if you will. Or you could use a CSR that is called mtime and read from that, and you should get the very same value. Well, at runtime, you can't really do that and compare them. Like you can't do it one way and the other way and compare them because the time is running, right? So you would always get some higher value from the second read. But yeah, nevertheless, yeah, these are now convenience helpers to actually, you know, get that information. And this is what I'm going to upstream to oreboot. Now there's one more thing which is very special and that actually bit me again. And that is this here. So based on the PLIC base, so, you know, we get this PLIC base here. The PLIC base is, yeah, this is actually the PLIC base, right? So we have the PLIC base, and then from there standardized is the offset of the clint. That's how it works. Let's actually change the comment here. So reflects the base address of the PLIC to which base address of the MMIO based PLIC to which the clint base address is relative to. Let's add a line break here. I should see that I get the 80 column indicator here. Relative to based on defined offset. Oh, we do have the offsets here, right? So yeah, the clint base offset is up here. Yeah, we didn't make that up. It's pretty standardized. Yeah, but what is again special now in XuanTie is the PLIC permission control register. So with that register, you would delegate access to the PLIC down to S mode. So usually in S mode, you would otherwise not be able to use the PLIC. And this way, Linux can actually do it and you know, access the PLIC and set up its own things. I'm actually not sure if that is maybe also standardized in the wider RISC-V ecosystem. To my knowledge, it is not. But yeah, anyway. So yeah, well, we we get the base address for the PLIC here, and we exposed yet another convenience function, which is just called initPLIC, and calling initPLIC would then mean, that we grant the access permission. And now let's actually have a look here. It is in our SBI platform implementation. So the SBI platform implementation is where we actually set up the timer and everything, and this is now per SoC. So yeah, that's I can't really meaningfully put that in the shared XuanTie crate, right? So there is a few things here that we will actually need to do, like per platform. Yeah, we might be able to extract a few things at some point, but yeah, whatever. Yeah, you also see we have this enable M timer clock over here. Are we invoking that function? We are, in fact. Yeah, the thing is, this is actually not only tied to the SBI, but we could also use the M timer in other places. So let's actually move that out here. I don't really want to have that in the SBI platform implementation. So I will put it here in main. So yeah, I will do this here. And instead of, what was it? Yeah, instead of doing enable M timer clock over here, I will actually do it in the payload stage. Function. So here in exec payload. So I will do init CSRs, and before that I will do enable M timer clock. I mean, I could also do it in the main function. Essentially, we don't really have to do this because we already did that in BT0. So, we could essentially print the time for the DRAM in it. Okay, I will just leave a comment here to do maybe move this somewhere else. Maybe move the timer in it somewhere else. Yeah, I will leave it at that. All right. So yeah, we need to have the timer enabled. We need to invoke the initPLIC function. We might want to rename that maybe at some point, because what it really does is, grant the access permission to the PLIC, not to the PLIC, but to S mode. Like the permission to access the PLIC is being delegated down to S mode. Well, granted to S mode, whatever. Yeah, we've actually been running for a while here now. I don't even know what time we started at. I think it's already been like a good hour now. Yeah, we're not gonna continue too much longer. I will just briefly walk you through the rest of this here. So yeah, we're doing init PMP. This is where we set up the protection for our own range. So that would be the range between like the DRAM base address and the payload base. So that is where our code is in between, and that would get the right protection. And yeah, that is actually reflected by this value here. Yeah, we should also like work on a library for doing this sort of stuff, because yeah, that way it's a bit too complicated. I think we can actually do something already with the existing RISC-V crate. I'm just not sure how ergonomic that is. Yeah, I mean, we're just trying the raw values currently. Let's see. Maybe let's just quickly try it out if we can actually do this. So we say no CFG. Yeah, the autocomplete is not yet ideal. So we would say try set PMP, and then you would have a usize, a range, a permission, and some boolean. Set the PMP configuration corresponding to the index. I I have no idea what the, so the index would be like 0 for the first one. So that would be like PMP CFG 0. I don't know how to express the range here and the permission and the locked bit. Yeah, we will need to look a bit at the API here. Great. So this is behind a macro. Actually want this function. Can we like jump to file? There we go. Alrighty. So setPMP would of course just try setPMP and unwrap, so we don't have to do that ourselves. And hello, can we go to that definition? Okay. Oh, it's already done here. Alrighty, so index is a usize, that is fine. And what would it do? Alright, does this here try read and try write. If it's really like, you know, setting up the given index, it would actually need to write to 2 registers. So it would need to write to the configuration register, which has like the configuration for each and every range, and then to the respective 2 values for the range. I don't know. It's a bit weird. And that's why I'm doing it by hand currently, because yeah, I haven't really understood that yet. Huh. All right, so range. Where is range used? Can we get this highlighted there? Range as usize. Shifted by 3. Huh. Oh. This here is just writing to the PMP configuration register. So huh. Yeah, I don't know. I will need to read up on that. Let's just not do that right away here. Let's just remove that line again. That's for some other day. Let's look at the rest of the implementation because it's really straightforward, and I'm sorry because this is scrolling so fast. Yeah, so the timer. The timer is pretty simple. Just ignore the debug print here. So there's 2 things we need to do for setting a timer. We clear the current timer, and then we write the new value for it. And well, the value just, you know, it needs to be written to the right register, and the register can be obtained by getting the right compare register and then adding the offset for the given heart. Well, and then we enable our timer again. So we actually need to do 3 things. Clear the timer, like the pending bit, and set the new value, and then enable the timer again. Because you know, when we enter this function, the timer should actually be disabled. That's what we actually do on the other side in our general SBI functions. Alrighty. Yeah, and those functions here, they are now actually the ones that we do not need to have in here. So let us remove this very horrible code up here. We can keep that part for later. Yeah, I would just keep that for the time being. Whoops. So what we are going to do now is we need to import this function. Is it really called get mtime compare register? We will see. So we are saying oops, we use the arc. No, it's oreboot arc RISC-V XuanTie, and then get mtime compare function, And there we have it. Right, that was it. Easy. Yeah, we can put that up here. There we go. Do we have anything else using the functions that we had in this file earlier? I think not. Yeah, it was just a leftover essentially. Yeah, looking good, looking good, looking good. So that means we can actually run our code again, and it should work just the same. So I'm turning it on again, and we should already be seeing everything happening again on the right-hand side as we saw earlier. And there we go. We are back in Linux again. Yeah, again, booting up in like seconds. There we go. All right. Yeah, and yeah, we can already CPU into it again, right? So we have our IP address and everything configured. So if we so wanted, we could again say, I don't know, we get our proxymd line. Yeah, that was a bit of a stun. So there's, well, that was actually quite quick right now. The first invocation of CPU can sometimes take a bit of a while because, you know, currently it generates a key on demand. I could put a pre-built or pre-generated key for the server in the DRAM file system. I haven't yet done that. Yeah, I don't know. Whatever, doesn't really matter. Anyway, so yeah, I hope what I've shown you earlier today was interesting. Just for completion, there is one more tiny thing I want to show you in the end. That is over here. So yeah, as I told you, very, very slowly, there is now patches coming into the mainline kernel. One of them is this year, and this is for the K230 clock controller. So yeah, as you can see here, the patches are a very recent submission. So this is from the 17th of February. Today's the 25th. So yeah, it's just been roughly a week since then. Well, and it just turned over to 25th here. So yeah, because it's just past midnight. Well, an hour past midnight. Anyway, yeah, with that, thank you very much for tuning in again. Yeah, go check out this board if you're interested in it. Yeah, most of what I just showed you is already in upstream oreboot. And yeah, as I just told you, I'm going to upstream, you know, a good handful of the helper functions that we just imported in our code for the board, well, or the SoC rather. And yeah, with that, let's stay in touch. I'm not sure yet when I will do the next live stream here. Yeah, I need to figure out a bit because yeah, there is still a bunch of things happening right now. You know, I'm involved in a few conferences and attending a bunch more over the next few weeks and months again. So yeah, I will have to see a bit. Anyway, with that, thank you very, very much. Take care and see you next time.